Last lecture, I explained the derivation of a CRC column curve. From the CRC column curve, we derive ASD curve and PD curve. Let's look at the ASD curve. ASD curve is equal to CRC curve divided by factor of safety. The factor of safety is 5 over 3 plus 3 over 8 KL over R over CC 1 over 8 KL over R CC cube, like that. If you rewrite in terms of lambda C, you can rewrite like that. This is CRC column curve. And then ASD curve is equal to CRC column curve divided by factor of safety. If KL equal to 0, that value is 0.6. Okay, 0.6. This is factor of safety. If you see here, if KL over R equals 0, that means factor of safety is 5 over 3. If we divide by 5 over 3, that means 0.6. Okay? CRC column curve. We can we can express in terms of slenderness ratio or lambda C, slenderness parameter. And then if lambda C is greater than square root 2, that means elastic lesion. This lesion, elastic lesion. This gap is a safety factor. So here, in the case, the safety factor is 23 over 12. It is almost 1.92, is almost constant regarding some elastic range. So if you input square root 2 here and calculate this term, then it results in 23 over 12. Okay, it is safety factor. So why should we apply the safety factor? Because in CRC column curve derivation, it does not consider geometry imperfection, right? CRC column curve just consider residual stresses, but not geometry imperfection, okay? But real column has geometry imperfection. That means initially not straight. That is geometry imperfection. So in order to consider geometry imperfection and load eccentricity, when we calculate in the paper, we consider load applied at the center, but the situation is not. So load usually has its eccentricity. So in order to consider those two factors, this set factor must be applied for CRC curve. That is AS curve, allowed stress design curve. The design format can be written like that. Rn equal nominal strength. Okay, nominal strength. That is simulated by CRC curve. Divided by safety factor, it is design strength. Okay, simulated by ASD curve. Okay, that is ASD curve. It is another term is that allowable stress greater than member stress. Okay, due to this service load. And then what is PD curve? PD means plastic design curve. That is ASD curve times 1.7. That is the plastic design curve. Plastic design curve is applied only for inelastic lesion. The name itself include inelastic concept, right? Plastic means inelastic. Okay, so only inelastic lesion, PD curve exists. So that means, as I mentioned, ASD curve times 1.7. That is PD curve. It exists only in elastic lesion because it is a plastic design. Plastic means inelastic. So here, from this design format, left hand side, the strength is 1.7. And then right hand side, there is load factor. For dead and live load factor is 1.7. For different load combination, this load factor will vary, will be different. That is the plastic design curve. Let's look at SSRC curve, structural stability research council curve. If we recall again, from CRC curve, ASD curve comes. From AS curve, PD curve comes. CRC curve is a bifurcation concept. So we consider perfectly straight, no geometry imperfection, but it considers residual stresses. But I'd like to introduce the SSRC curve. So in SSRC curve, Structural Stability Research Council curve. This committee comes from CRC committee. So originally the name of the committee is CRC, but that the name of the committee has been changed to SSRC. So we call it SSRC curve. This committee developed its own column curve. It is called SSRC curve. SSRC curve consider geometry imperfection. The imperfection magnitude is 0.001 L and residual stresses together. CRC curve only consider residual stresses, okay? But SSRC curve consider not only residual stresses but also geometry imperfection. If I draw the shape of that geometry imperfection, is this 0.00 L. That means this is L, something like that, and then there is geometry imperfection like that. The maximum magnitude, this magnitude is 0.001 L. That is the imperfection. In developing SSH curve, they used computer analysis and test for 112 columns. So they developed multiple column curves: wide frame section, box section, hot roll section, rail section, heavy section, light section. Heavy means the thickness is thick. Light section is thickness is thin. Regarding strong axis, weak axis, develop multiple column curves using 112 columns. If you see page 126, you can see curve 1 to 3 based on equation 2.11.8 AC. From this result, analysis and test result, they make curve fitting. If I draw roughly, they introduce 3 different SSH curve. 1, 2, 3. So they make some category, okay? The different sections, strong axis, weak axis, heavy light section, like that. So they make 1, 2, 3 for the different type of sections. Yeah, and then firstly they develop SSH curve 1 to 3, and then they make curve fitting to define LRFD column curve like that. As you see, LRFD column curve is a little higher than SSH curve 2. So considering economy, that means if we make LRFD curve above than average, okay, then the steel section can be designed somewhat smaller section, okay, because the strength is somewhat higher than average of SSH curve. If we determine this LRFD curve somewhat lower than average, then steel section must be larger. So then steel is less competitive. In that time, the considering steel industry economy, they determine a little higher curve of this SSIC average curve strength. So they finally determine like that, P of POI equal like this. As I mentioned before, LRFT curve consider the geometry imperfection. That means LRFT use low diffraction analysis in its development, right? They use single column curve. Firstly, they developed 3 different curves. But for designer, it is somewhat complicated to use 3 different curves for different sections. So they determine just one design curve. That is LRFT curve. Okay, for design easiness, comparable to SSRC curve 2. A little the higher strength is used. The design format like this: pi Rn greater than sigma gamma Qni. Rn is nominal resistance, Qn equal load effect, pi equal resistance factor, gamma equal load factor. So in order to determine resistance factor and load factor, the probabilistic concept has been used. So Among ASD, PD, LRFD, the most advanced column curve is LRFD curve because they use the probabilistic concept, and then they use some different load factor is used for different load, considering the characteristic of different load type. I mean some dead load and live load. So the variation of dead load is somewhat small. So usually load factor is 1.2. The variation of live load is very large. So load factor is used the value of 1.6 like that. Okay, so that kind of probabilistic concept is used. I would like to show some example for your understanding of design curve. Yeah, that is a problem 2.11, double section. In Korea, we call it the H section. In America, double section. Double section means this flange is wide, so wide flange section. So the name is double section. Narrow flange section is called I section in America. And pin and column, as you see, placed and mid height in weak direction. This is a weak axis and strong axis. At the middle, there is some brace in weak axis. Strong axis, just top and bottom. So load, this live load 60. Another live load, that is loop load, is 40, and dead load is 60. Sigma y equal 36 ksi. So we have to determine appropriate section using different design approach, ASD, PD, and LRFD. Let's look at the ASD format. Yeah, that is the ASD format if you remember, right? Yeah. So Rn over Fs. Fs is a safety factor. And then Qni is member stress. This is allowed stress. That is the concept. So allowed stress design format. P over Py can be written this form. AS curve divided by safety factor, right? That is AS curve. If gamma c less than square root 2, that is inelastic region. This elastic region curve like that. Here we calculate sigma Qni 60, 40, 60. Okay, the load, total load 160 kips. So we try W wide frame section 10 times 30. This 30 means pound per feet. 10 means 10 inch height. Area is this one, gamma x, gamma y, like that. And then let's calculate strong axis first. So we have to calculate lambda c. So Rx KL x square root 2 sigma y pi square e. So if you input these values, radius of gyration in strong axis, square root 2, yeah, these values, then 0.369 is less than square root 2. So is it elastic or inelastic color? Inelastic. So we have to use this curve. Input these values, every values, then you can get 174.4 kips, greater than 160. So okay. Let's calculate weak axis. So this equation, so different thing is that this Ry is different, and then length is different. Strong axis is 12 feet, but in weak axis we have some brace at mid height. Okay, that's 6 feet. Square root like that, 0.589 less than square root 2. That means inelastic column. So we have to use this equation, that value slightly greater than the load, apply load. So we can use wide flange W 10 by 30. Let's look at the PD format. PD format is left hand side we multiply 1.7. Do you remember? PD curve is made by ASD curve times 1.7. And right hand side we have to use load factor here. So from this one is just ASD curve, right? Times 1.7. Then PD column curve if less than square root 2. The load combination of live and dead load factor is 1.7 in PD plus design. If you input this 1.7. Left hand side is 1.7, right hand side is 1.7. In that case, it can be cancelled out. Then it becomes to ASD, column curve, in this specific case. So the result must be same to ASD equation. So we can use right plane section 10 times 30. In a specific case, the result is with identical to ASD. But if the load combination is different, let's say live and earthquake, so live and wind load, the load factor must be changed. Then result must be changed. Okay, so let's look at the LRFD format. LRFD format is this one. It is very typical. Okay, pi Rn should be greater than sigma gamma I qn I. In elastic range, the column curve can be written like this. Elastic range column curve is this. If we use the load combination, these three, dead load 1.4, dead load, live load, loop load, like that. Okay, dead load, loop load, live load, like that. That is load combination of LRFD. Okay, so we can calculate this value, this value, this value. So maximum factor load is 188 kips. For column, we have to use pi is equal to 0.85. So try double section 10 times 26. A, gamma x, gamma y. Okay, radius of gyration. So if we calculate the strong axis, lambda c can be calculated as 0.371. Is less than 1.5. That means inelastic column. So pi Rn equal pi exponential blah blah blah. If you input these values here, you can get 220.8 kips. It is greater than 888 kips, so it's okay. Let's calculate weak axis. Okay, the length is just half of the strong axis because there is a brace at mid height. Lambda c equal this value, and the pi Rn a exponential something like that is greater than 188 kips. So we can use W 10 by 26. That is LRFD design approach. Do you understand? So far we study column curves. We have some time, so I'd like to provide you some keys. The column has geometry imperfection like that. This is delta 0. This is delta 0. And then apply load P here. Let's consider this is just elastic column, not inelastic. What is PCR of this column? Geometry imperfection like that. What is PCR? Delta 0. What is maximum? Maximum P. In fact, there is some geometry imperfection. We don't have any PCR, right? But what is the maximum P? In this case, maximum P, L square, pi square EI, right? A little less than pi square EI over L square because there is some geometry imperfection. So if we draw the curve P and delta, if there is no geometry imperfection, if this kind of straight column, we have a PCR here. But if we have some geometry imperfection here, then we have some buckle like that. So we can draw the strength curve like that. Then how about the geometry imperfection like this? Then what is the maximum P? Maximum P that we can apply. Can you answer? That is P equal L square 4 pi square EI. That is answer. How many answer like this? That means 4 times, something like that. Do you think it is possible? If the initial imperfection like this, we have the maximum P is this one, okay? Not that one. Because if we apply the load like that, the imperfection increase like that, and then increase some more load, this column buckle like this. The shape of the buckling, change it like this. So maximum PCR is like that. If we make geometry information like this, then if you get the about 4 times the PCR, then everybody try to make the geometry information like that. But the fact is, it buckle. The mode shape changes like that. So maximum P equal pi square EI over L square, this value. So it is keys. See you next time.